Hello and most welcome to 1294 of the H series, and I will continue as I started in 1293 with intuitionist mathematics or constructivist mathematics if you prefer. It is three people that you need to remember the most when it comes to the construction. It is Poincaré, Brauer, and then you have Bishop. I also have contact with Newcomb Greenleaf, who's the inheritor of the legacy of constructivist mathematics. Shortly said, constructivist mathematics is having problem with the law of the excluded middle. This might sound insignificant, some pointy detail, but it is very far from insignificant. I would say it could be the most significant thing of all. And even to discover it, what it is doing with our thinking, is in itself a journey. Troublesome journey at the start. We've been doing constructive mathematics for 6 years now, since I started to get really interested. There's also a video on YouTube made by a Slovenian professor, I think it is. 5 stages of accepting constructive mathematics. It's a very good primer. It's full of humor, and it also goes to show the troublesome road to speak to get to constructive mathematics. It is a chore, but I tell you, it's well worth it. It's well worth it. It has several advantages. Let's see if we can change the lighting here. Just give me a chance. It has a lot of advantages, and once you starting to understand, the benefits are immensely. Possibly the most beneficial thing is that the law of the excluded middle will stop haunting you in all the other areas outside of mathematics. And in those areas, the law of the excluded middle, I would say, is impossible to discover. It's absolutely ingrained in our thinking. It's part and parcel of thinking. It is part and parcel of being human. So I would say there is no getting around that part. But mathematics is a shortcut in a way. It makes the segue into the new thinking easier, manageable. Something that could not be experienced, understanding that the law of the excluded middle needs to be used consciously, and used unconsciously it will have disastrous consequences. We did mention before explosion. Explosion means that everything becomes possible. An explosion has not been properly directed, talked about. It has not been a part of common parlance. Oh dear, what's happening here? It's been outside of discourse, probably for very good reasons, but it needs to enter once more. And it needs to be able to do its work in a proper way. Left to its own business, it can do, there is no limit to what it can do. I will continue to take a look at intuitionist and constructive mathematics through the eyes of Brouwer specifically. He was the constructor of something completely different as a start, something that made his fame. It is called a fixed point theorem. And you can develop it this way. Take first a flat sheet of paper and imagine the most fiendishly impossible maths homework or your worst enemy. Crumple it into a ball any way you please. Now lay this crumpled mess back on the spot where the original uncrumbled sheet of paper lay previously, and press it down until it is absolutely flat. Unbelievable as it may seem, there is a point on the crumbled sheet of paper which is back exactly in the same spot as it were before you did the crumbling. This result is known as a fixed point theorem, since it shows that when one thing is transformed into another, in this case the flat sheet of paper is transformed into the crumbled one, there is a point which is fixed under the transformation, a point which does not change its position when the transformation is performed. In fact, Brouwer's result was not the only fixed point theorem, but was a very powerful one. It applies to any plane area which can be continuously transformed into a disk. In other words, any closed shape in the plane in a single piece and without bits missing from it. Any such shape has a fixed point when it is continuously transformed to itself. Here, a continuous transformation means that some parts can be stretched or compressed or even folded on to themselves, but no tears or holes can be made. To be transformed to itself means that the resulting shape can be made to occupy the same space as the untransformed shape did. Indeed, Brouwer showed that the same is true in any dimension. This means that when a sphere is transformed onto itself, it has a fixed point. When a child takes a globe of Play-Doh and rolls it into a snake, at least one point remains fixed. And this is true of a 27-dimensional child making a 27-dimensional snake from a 27-dimensional globe of Play-Doh. It definitely exists, but where? Surprising this result may be, but it seems hardly likely to start a revolution. Surprising results occur surprisingly often in mathematics. A surprising result in itself, you might say. Even Brouwer's proof used a standard and unsurprising approach not considered controversial at the time, and not often considered controversial today. However, it was this type of proof, known as an existence proof, which Brouwer and his movement reject. in this type of proof, the object you are considering, in this case a fixed point, is shown to exists with certainty. However, the proof says nothing whatsoever about where the object exists or how to find it. The treasure is certainly buried, but there is no X to mark the spot. This is like saying that if a paper aeroplane hits the teacher, she is certain that someone in the class flew it, but she has no way of finding out who is the guilty culprit. The notion of proving only the existence of an object was soon rejected outright by Brouwer, and he started to claim that only those objects which can actually construct should be believed. By construct, Brouwer did not mean a model made from wire and papier-mâché, but rather a mathematical algorithm, a recipe for determining all of the features of an object. In so doing, you also get existence for free. Of course, because if you construct an object, then it certainly exists. A constructive proof of a fixed point theorem would tell you exactly where the fixed point is, exactly where X should mark the spot. If another theorem deals with a certain number, say the biggest element of a set of numbers, a constructivist proof would not merely say that the number exists, but would rather tell you exactly what that number is, or how to calculate it. This is usually acknowledged to be the birth of constructivism or intuitionism in mathematics. Both names are used interchangeably, even though neither gives the whole picture. Constructivism is a movement in the foundations of mathematics, which holds that only those objects which can be constructed in the human mind from an undeniable true thought processes are to be believed. In this way, it harks back to Immanuel Kant and his claim that intuition alone tells us that the basics of mathematics are true. Indeed, the constructivist school has since been built on the foundation of what is known as intuitionistic logic, to distinguish it from traditional or classical logic. Take my sweater off. Did you or didn't you? And I've given a private name to this chapter. Have you stopped beating your wife? Yes, we're getting into contradictions. In the real world, if a teacher confronts you and says, "Did you throw this paper airplane?" or "Didn't you?" the correct answer is always yes. This is because either you threw it or you didn't throw it. So a question which asks if you did either of these things must have a positive answer. If A represents a statement such as "I threw the paper aeroplane," the only options seem to be A or not A, the letter being the opposite of A. If we write not A as negative A, then it would seem unreasonable to suppose that there is a third option beyond A and not A. This is known in classical logic as the law of the excluded middle, or usually acronymed LEM for short. It says that there is no middle ground between A and negative A. What distinguishes intuitionist logic from classical logic is the rejection of the LEM. And here is a depiction of a truth table, but I think you all know how they look. This deceptively simple distinction disguises a profound difference in viewpoint about truth and meaning. Someone who believes in classical logic is known as a Platonist or a realist. From the realist viewpoint, which is certainly the way you and I were taught mathematics and logic, the truth of a statement is determined by truth tables. If my statement reads A or negative A, then I look at the possible values of the bits which compose the statement, and then at how the logical operators combine those values to give the truth or falsity of the whole statement. For example, if A is true, then not A is false, and the OR operator says that P or Q is true. When either P or Q are true. So in this case, A or negative A is true. The only other option is that A is false, but then negative A is true, and again A or negative A is true. The statement must be true because either I threw the airplane or I did not. But this argument rests on the idea that a statement is either true or false, which is known as bivalence. Intuitionists reject the validity of bivalence in mathematics. Why? Well, an intuitionist believes that a mathematical statement is made true or false by the construction of a proof. In other words, a mathematical statement has no truth table value before a proof has been constructed. It is not so much that a statement exists in some weird middle ground between true and false, but rather that truth or falsity is a quality given to a statement by the construction of a proof by a human being. Using ideas and techniques of mathematics which are intuitively self-evident to the human mind. As such, bivalence is rejected, and therefore so is the law of the excluded middle. Pie in the sky. As an illustration, consider Brouwer's example based on the familiar number pi. Brouwer used pi to provide what he claims to be a counterexample to the law of trichotomy. That law which states that every real number is either positive, negative, or zero. quite a claim. And here is how he made it. There will always be simple questions we can ask about pi. The answers to which we do not yet know. Fortunately, there are well-known algorithms for generating as many digits of pi as we like. So questions like, are there ever 100 consecutive zeros in the decimal expansion of pi, may be answered in the affirmative one day when we have sufficient computing power to follow the algorithms through to a large number of digits. But if we have never yet found 100 consecutive zeros, then we can't say that there is no such run of zeros. In this way, we can always formulate a question such as this: be it 100 zeros or 457 sixes, or what have you. Let S be one of those statements. Maybe there are 100 consecutive zeros in the decimal expansion of pi. To most mathematicians, and I suspect most of you, the statement S or not S is true. That is, even if we haven't yet found the place in the decimal expansion of pi where 100 zeros occur. Either it is lurking there, waiting for our chugging computers to get it, or it does not exist at all. But a constructivist disagree. Because of her rejection of the law of the excluded middle, the constructivists argues that it is a mistake to think of the decimal expansion of existing out there, somewhere as an object independent of the human mind. To the constructivist, the decimal expansion of pi only exists up to the truncated point to which it has been calculated by humans or our proxies, the computers. Things get even worse for the realist. Better for the constructivist when we bring in Brouwer's number pi hat. Suppose, he said, that we go on calculating pi until we find the first run of 100 consecutive zeros. If it starts at the 9th decimal place and n is odd, let pi hat terminate at its 9th digit. If n is even, let the n plus 1 digit of pi hat be 1, and then terminate its decimal expansion. The key points to bear in mind are the following. We have a perfectly decent construction for pi hat. Just calculate pi and let the two numbers be equal. Until we hit a run of 100 zeros in pi. At which point follow the rules above. We do not know at present, and probably never will, whether such an even exists. No matter, we can still discuss the quantity Q, which is pi hat minus pi. If no run of 100 consecutive zeros ever appears, then pi hat is the same as pi and q. If such a run appears and begins at an even place in the expansion, then pi hat is bigger than pi, and q will be bigger than 0. If at an odd place, then q is less than 0. The problem is if after a billion years of calculating billions of digits of pi, we still have not found a run of 100 consecutive zeros, then we still do not know whether q is positive, negative, or 0, and are no closer whatsoever to an answer. But the law of trichotomy, from a classical standpoint, asserts that q is either positive, negative, or 0, regardless of the fact that we will never know which. In other words, there are situations in which we can never determine, even in principle, whether a number is positive, negative, or 0, and yet the law of trichotomy would insist that one must be real. What meaning can we give to this law when such a simple construction reveals it to be effectively meaningless? A constructivist says that Q will be one of the three when, and that is a big if, we ever get to a run of 100 zeros, but is none of them beforehand. The disturbing fact for realists is that this implies that mathematics is subjective and time dependent. Indeed, that it is also dependent on such messy things as history and culture. Most mathematicians quickly reject this argument and say instead that Q is either positive, negative, or zero. We simply don't know which. This illustrates how firmly entrenched is the realist view that mathematical objects exists independently of the human mind out there, somewhere, just waiting to be discovered. Even in our everyday conception of objects as fundamental as the real numbers, intuitionism is radically anti-realist. Anti-realist in that it claims mathematical objects only come in existence once they are constructed by a human mind. And radical, since it seeks to recast all of mathematics in this light. We have looked here at a couple of telling examples of the problems constructivists see in the realist view of mathematics, and much more on this fascinating topic and its history can be found in the suggested reading below. What has been the effect on modern mathematics of this revelatory and revolutionary viewpoint? Surprisingly little, which is surprising in itself. Mathematics is still taught with an underpinning explicitly acknowledged or not of a realist classical logic. Proof by contradiction, existence proof, and other methods and types of proof shown to rest on shaky foundations by the constructivists are still taught as standard to undergraduates around the world at even the earliest stages in our schools. Children are taught implicitly of numbers as existing independently of human minds and awaiting discovery. Professional mathematicians tend largely to ignore the issue. The only emotion constructivist arguments elicit tending to be annoyance. The jury is still out on whether mathematics exists independently of us or is purely a product of the human mind, or some combination of the two. But to assume knowledge of the verdict before it has been delivered to us is to resort to reliance on faith, which even the realists would usually reject. And that concludes constructive mathematics from this anonymous writer. And I will now continue with Stephen M Rosen. It's about time. Also on request from my colleagues. He writes about quantum gravity and compares it to phenomenological philosophy. And be duly noted that phenomenological is some phrase also used within quantum physics. But now he's stretching out to philosophy. Abstract. The central thesis of this paper is that contemporary theoretical physics is grounded in philosophical presuppositions that make it difficult to effectively address the problems of subject-object interaction and discontinuity inherent in quantum gravity. The core objectivist assumption implicit in relativity theory and quantum mechanics is uncovered, and we see that in string theory. This assumption leads into contradiction. To address this challenge, a new philosophical foundation is proposed based on the phenomenology of Maurice Merleau-Ponty and Martin Heidegger. Then, through the application of qualitative topology and hypernumbers, phenomenological ideas about space, time, and dimension are brought into focus so as to provide specific solutions to the problems of force field generation and unification. The phenomenological string theory that results speaks to the inconclusiveness of conventional string theory and resolves its core contradiction. Introduction. Over 2,000 years ago, Plato laid down a tripartite formula that would be tacitly incorporated into the foundations of modern science and into Western culture at large. In a key passage of the Timaeus, he states, we must make a threefold distinction and think of that which becomes, that in which it becomes, and the model which it resembles. The first term refers to any particular object that is discernible through the senses. Plato speaks of the second term, that in which an object becomes as the receptacle, describing it as the vessel that contains the changing forms or objects without itself changing. A little later, he characterizes this receptacle as space. Finally, the model for the transitory object is the eternal object, the changeless form or archetype. This perfect form is eidos, a rational idea or ordering principle in the mind of the demiurge. Using these, his archetypal thoughts as his blueprints, the divine creator fashions an orderly world of particular objects and events. The third term brings in the element of subjectivity. Though the subject is divinely personified in the Timaeus centuries later, with the Renaissance and the philosophy of René Descartes, subjectivity took on a more secular and general character. According to Descartes, whereas the object is res extensa, a thing extended in space, the subject is res cogitans, a thinking thing entirely without spatial extension. The threefold template, thus adumbrated by Plato and carried forward in succeeding centuries, is that of object, in space before subject. The object is what is experienced. The subject is the transcendent perspective from which the experience is had. And space is the continuous medium through which the experience occurs. The relationship among these three terms is that of categorical division. By the time the Renaissance was over, the tripartite classical formula was firmly entrenched in human affairs and had assumed the status of a self-evident intuition. All human perception was now generally organized in terms of objects appearing in space before the gaze of detached subject. The formula is clearly in evidence in the domain of scientific analysis, where Descartes' philosophy is transposed into Cartesian mathematics via his system of coordinates. And these can be accurately compared to see exactly how the formula applies. Let us focus on a feature implicit in Plato's original account. While the object is transitory, the subject and the space in which it operates are not. This finds expression in all graphed equations. Consider the simple example of the equation for a parabola. There is a depiction. In the graph of the equation, x and y are variables, terms whose specific values change from point to point in the xy coordinate system. The variables correspond to the object term in the tripartite schema, while the coordinate system itself constitutes the invariant spatial framework in which the objects are embedded. The third term of the classical formula versus the subject can also be located in the graph, at least indirectly. At the center of the XY coordinate system is the 0.0 origin, the origo. The origin of the function space plays a unique role, representing the locus of which analysis or observation begins. Origo serves, in effect, as the surrogate for the subject's eyes, for the fixed point of view from which empirical observations are made or analyses carried out. There is, of course, another key feature of the equation. By definition, the variables of the equation undergo change, but the relationship between these variables does not. The equation thus expresses what remains invariant when particular values in the coordinate system are transformed. The invariance of the equation mediates between the variability of the particular objects and the invariance of the subject and its space. We may say that the analytical subject brings order to the objects it encounters in space by imposing abstract invariance upon their concrete variability. Note that the equation's invariance clearly depends on the continuity of the functional space in which the relationship between variables is graphed. Were there a breach in the continuum at this singular point, the relationship would be abrogated and the equation would assume a non-finite value. So whatever transformations of objects' variables may occur within the spatial container, for the relationships between variables to be rendered invariant, the container itself must be invariant. It must stay intact, retain its continuity. Though physics has been revolutionized since the days of Descartes, at bottom the old formula continues to operate, while the Michelson-Morley experiment indicated that Maxwell's equations for electromagnetism could not be shown to be invariant with respect to the classical dimensions of space and time. Einstein soon stepped in to demonstrate that the invariance of the equations could be established within a new and integrated framework of space-time. In special relativity, the equations for electromagnetic interaction remain invariant under global transformations of space-time coordinates. Generally speaking, then, relativity theory accounts for physical interactions by allowing the all space and time to vary within a new, more abstract context of changeless space-time. As for the relationship between subject and object, it is instructive to compare pre-Einsteinian and Einsteinian cases. In the former, it was possible to assume a universal observer, a Laplacian demon. All objective events occurring in three-dimensional space were cast before the gaze of this idealized subject. What Einstein was able to demonstrate is that when it comes to phenomena whose velocities approach the velocity of light. The local space and time of the concrete observer can no longer be discounted. Of course, Einstein did not simply accept the intrinsic variability of concrete observation. In his revision of classical physics, concrete observation itself is explicitly included in the account of nature by making this subjectivity into a new object and whose transformations are invariant in a higher dimensional context. So with Einstein, the objects under scrutiny are now observational events transpiring in a four-dimensional space-time, whereas three-dimensional events are concretely observable. The fourth dimension of Einsteinian relativity is an abstraction. The higher order Einsteinian observer of these four-dimensional acts of observation is therefore a further step removed from concrete reality than was his Cartesian predecessors. Nevertheless, in both cases, the traditional stance is strictly maintained. In both, we have object in space before subject. But doesn't the old formula break down in the other major revolution of modern physics? Does not the core discontinuity and accompanying subject-object interaction of quantum mechanics fly in the face of classical intuition? In the Copenhagen interpretation of quantum mechanics, a pragmatic approach is taken to this. No doubt the discontinuity lying at the heart of quantum theory entails a built-in limitation to the precision of objective measurement. Yet uncertainty effects are readily manageable via probabilistic analysis, as long as the phenomena under study are scaled well above the Planck length. With this condition met, the classical formula can continue to operate as the default assumption. However, beginning in the last quarter of the 20th century, the condition could no longer be met. Before the 1970s, quantum physical research focused on the study of non-gravitational forces, strong, weak, and electromagnetic, whose scale of operation exceeded the Planck length by a considerable margin. But as research progressed, physicists became more determined to arrive at a unified description of the seemingly diverse forces. Generally speaking, contemporary field theory associates the unification of nature's forces with a hotter, denser, microscopically scaled universe. The greater the number of forces to be unified, the higher the unification energy, and the smaller the scale of magnitude at which the forces operate. In the 1970s, with electromagnetic and weak nuclear forces having been unified, and advances made toward a grand unification of the free non-gravitational forces, physicists turn their attention to gravity. Now, in seeking to combine all four forces of nature in a single account, researchers could no longer avoid the ultramicroscopic Planck scale, wherein uncertainty becomes uncontrollable and probabilistic analysis breaks down. I venture to say that little significant progress has been made in the 30 years since the problem of quantum gravity first gained serious attention. To be sure, ambitious projects have been undertaken in this regard. Most notably, string theory. This has been the dominant approach, generating prodigious amounts of mathematical research and much excitement in the theoretical physics community. I have offered a detailed critique of string theory elsewhere, and some of my own objections are reflected in 2 recent books on the subject. At present, I will limit myself to addressing 2 major problems with the theory, one real and the other apparent. According to string theory, the fundamental constituents of the physical universe are not zero-dimensional point particles, as previously supposed, but one-dimensional strings. The positing of fundamental vibrating strings is not motivated by empirical observation, nor is it based on positive theoretical insight as much as on a negative consideration. Whereas the supposition of a vanishingly small point particles leads one to probe below the Planck length into the forbidden zone of unmanageable energies and nonsensical equations. The assumptions of string-like elements whose finite extension is no smaller than the Planck length allows one to avoid such a pitfall. But while the general equations of string theory are expressively designed to eliminate the ambiguities of the trans-Planckian world, ambiguity is carried forward epistemically, making it its present felt in the vast multiplicity of possible solutions to those equations. with no provision of guiding principles by means of which the field of possibilities can be reduced. Beyond this problem, an apparent contradiction lies at the heart of string theory. We are going to see that while this inconsistency at first may seem only to hammer another nail into string theory's coffin, in fact, it may point toward the theory's redemption, albeit in a very different form. Second paragraph. Apparent self-contradictions of string theory and its philosophical implications. Brian Greene emphasizes that the spatially extended nature of a string is the crucial new element allowing for a single harmonious framework incorporating both gravitational and quantum mechanical theories. But does the notion of a fundamental particle with finite extension make sense? Strings are truly fundamental, says Greene. They are atoms, uncuttable constituents of nature. So even though strings have spatial extent, the question of their composition is without any content. Is there not a contradiction here? For at least according to the classical concept of the continuum, not explicitly challenged by string theory, to be an object extended in space, to be cuttable, in fact, infinitely divisible. How could then a string be a fundamental particle, an indivisible ingredient of nature, when it is spatially extended thus divisible. Let us look more closely at why string theory is led into such a contradiction for conventional thinking. Within the classical framework of object in space before subject, the idea of an indivisible point-like atom or particle is indispensable in order for the subject to analyze effectively an object in space. He must be able to determine what the object is made of, what its basic constituents are. There is a categorical difference between the atomic constituents of an object and the object itself. That is because, by definition, the atoms of which an object is composed, being indivisible, are not themselves open to analysis. The idea is not to say what they are made of. Rather, they are the means by which the analysis of the object is performed. Therefore, the point-like elementary particles, instead of belonging with the object term of the classical formula, in fact belong with the subject term. The fundamental particle to which an object is reduced is the element upon which the subject's analysis of that object is built. The standard model of unification maintains the classical assumption of point particles by adopting the attitude of positivistic pragmatism found in the Copenhagen interpretation. Owing to the irreducibly uncertainty inherent in Planck's constant, it is true that the closer we come to the point-like atomic origin of observation and analysis, the fuzzier that origin becomes. Yet in non-gravitational quantum mechanics, the fuzzing out of the origin is tolerable, since the uncertainty can be managed through probabilistic approximation. There is no need to trouble ourselves with the meaning of the underlying uncertainty. What we don't know isn't hurting us in the practical activity of science that we engage in. Therefore, we don't have to think about it. For its part, string theory would also hope to effectively adopt a positivistic stance. We can't know what goes on below the fundamental Planck scale strings, so we are entitled to ignore it. However, whereas the non-gravitational approach can afford its positivism, it seems that string theory cannot, since its positivism must be brought or bought at the price of self-contradiction. And I think that is an excellent stopping point. I say thank you very much. Just put a pointer here. Can find a working pen. And I wish you, no, it's still morning. Wish you a very pleasant morning. Bye bye for now. Down in the dungeon.